Welcome, ladies and gentlemen. So, we're back again. Like, share, comment, subscribe. As always, guys, if you haven't done so already, check out the website, Eigenbros.com, Eigenbros on Instagram, Eigenbros on Twitter, Eigenbros2 on TikTok, and then patrons, guys. Thank you so much, as always. And if you guys want to become a patron, patreon.com/Eigenbros is our space, whatever you call it, in Patreon.
Yeah.
And we do a 30-minute podcast there every week. So you guys, if you want to have extra content, check that out. And yeah, just keeping it brief with the intro. Let's jump into it. So
Let's do it.
we're talking Euler-Lagrange equations. So this is one of these topics that I've been avoiding for a long time.
Yeah.
Because I'm kind of intimidated by it. It's like one of these really deep physics concepts and even math concepts. It's basically like one of the most important equations, I would say, in physics. It basically is like a master equation that gives you any, or ideally any kind of equation for the systems that we work with in, classical mechanics to quantum field theory to even quantum mechanics. I mean, the Lagrangian is everywhere.
Yeah.
Yeah, what are your thoughts about the Lagrangian before we start off, Juan?
I think it's cool.
And that wraps it up, ladies and gentlemen.
The end. No. Euler-Lagrange. Euler, not spelled how it sounds.
No. I probably called it Euler for a good year.
Same. It's German physicist. Euler?
Euler. Yeah, I think you're right.
Yeah. German guy. He
or maybe he's something else. I don't know.
Wasn't he like one of these savants?
Yeah.
He
literally did like everything in mathematics.
Yeah.
It's like a joke, like if mathematicians just name whatever a new math thing is after, or they name the second guy
Euler.
to do it because Euler is usually the guy who did it first. I fucked that up, but I think I got the point across.
You have to hyphenate your name
Yeah.
with Euler because
he probably already got to it at some point.
Because he owns you.
Yeah.
Yeah. No, I'm just kidding.
Yeah, we did an episode on Giga Chad physicist. That's the
Yeah.
Giga Chad of mathematics, basically.
Yeah, he is. He really is. He's actually I think he motivated people proving Fermat's theorem.
Oh, did he?
Because I think he was the guy who was like, "Oh, I have a proof for this, but it's actually too big to write in the margins here."
Well, that's what Fermat said.
No, this is what
No, that's what Fermat said. Fermat said that he had a proof for something, but he said it's too. It was too big.
You're right. You're right. Who the fuck am I thinking of? I thought Euler had a proof, but he also was like, yeah.
He might have said something similar, but what you're talking about is definitely Fermat because it's Fermat's last theorem.
Yeah. See, this is what sleep deprivation does to you folks.
Anyway, let's jump back on the Lagrangian. So what do you?
I mean, I kind of want to contextualize. I'm one of these people that feel like you kind of have to contextualize the people. You have to know the people who came up with it.
I see.
To know.
See, I'm trying to capture the audience in the first 15 minutes for the YouTube algorithm.
Gotcha.
So I'm trying to jump in,
Okay,
jump
gotcha.
in there.
Well, here's the thing. Lagrange, very useful. We use it for physics.
Yep.
If you haven't gotten that just yet. To solve dynamical equations, equations of motion. That's our bread and butter for physicists. We're in the market to predict stuff.
Right. So the equation of motions for, the people who are laymen, let's say, I mean, it's just like, it's the set of equations you need to basically predict anything about the motion of a system. So it's like you put in a number or you put in, let's say if you got you're walking down the street or let's say you have a chart of someone's path of a marathon or something, let's say. The equations of motion would be like you can have their position at any time, you can know their velocity, you can know their acceleration at any time. So it basically gives you all the information you need to know about how they moved along that path. So it's very powerful. You can see that, and it basically tells you everything you need to know about the dynamics of the system. So with that being said, though,
only if the energy is conserved.
Yeah.
Because I was gonna say, like if you try to counterpoint You know, if somebody's in the comments like, well, you know, actually, not every, you know, it's that is the caveat for a lot of stuff. It has to be there are conservative forces in physics and non-conservative forces. But
yeah, you kind of jumped the gun for me a little bit. I had a little order, but the thing is, you're right, because the Lagrangian is.
Oh, I was trying to summarize everything in the first 5 minutes.
That's good though. That's good though. No worries. Just just do what you feel.
No,
but yeah, it's like the. So let's just jump in. Like, what is the Lagrangian though? So Lagrangian, basically, like I said in the beginning, it's like the master equation, or I guess we'll call it the Euler-Lagrange equations. The Lagrangian is a part of the action. So there's something called the principle of least action, and the principle of least action is really, that's the main concept, that is the big one in physics, and the principle of least action basically seeks to minimize the energy of a system. So what does that mean exactly? So it's like if you're trying to figure out the lowest possible energy it takes to do some action, to literally do something. I shouldn't use the word action because it's gonna mix up the two meanings now. So it's like the minimal energy it takes to do something. The action is what you use to be able to minimize or find the minimal path, let's say, to do that thing. So I guess it's better to give examples usually with things like this. So like, let's say you throw a ball in the air, right? If you throw a ball in the air, what the action or the principle of least action tells you is that there is a path of minimal energy that ball will take. So there's only one path that ball will take, and it's always the least energy path, essentially. So you can imagine, like, if you threw the ball and we lived in some alternate reality where the ball did this zigzag motion, or, you know, did a loop-to-loop, you know, before it came back down. What the action basically tells you, the principle of least action tells you, is that the ball will never do the loop-to-loop of the zigzag. It's going to do the normal path that we're familiar with, just the up and the down, you know, because that's the minimal path it takes.
Yeah. Unless you're a baseball player and you throw curveballs.
Yeah, well, then you're just messing around with physics.
No, because you put spin on it. But those are initial condition stuff. But initial conditions, assuming that it's a projectile motion, right? It's just like, boom, like a cannonball, right?
Yeah.
Yeah.
Yeah, so it's just
nothing fancy.
No, it's nothing fancy. So it's just this weird thing, and it's not necessarily obvious, though. Like, to me, when I learned about the Lagrangian, it was kind of a mind-blowing situation because, you know, I didn't realize that there was something so fundamental about physics that you could say regarding energy. Because, you know, and this is another reason why I was kind of scared to talk about the Lagrangian, is because, you know, the action which contains the Lagrangian is equal to the kinetic energy minus the potential energy. And, you know, kinetic energy, of course, for the layman is energy that's moving, so it has to do with movement. It's the energy, like if you're punching someone in the face, you know, it's the energy of your fist. Or that's kind of violent, but
yeah, I was like, that's interesting. Interesting. That's your first. Imagine you punching someone in the face.
But yeah, that's
anyway. That's
kinetic energy.
Yeah.
And then potential energy.
Potential
would be
energy is in your fist.
Hey, that's true. That's right. Right. It's before you punch him in the face. It's all the rage that you're building in your fist. All right, let's stop the toxic masculinity.
Yeah, let's tone it down here a little bit.
Or the Eigenbros doesn't help.
Yeah, I know. Well, let's. But the kinetic energy is the energy in motion, and then it's succinctly captured in the 1/2 mv squared, so mass times velocity.
That's the classic
squared.
equation. Yeah, and then the potential energy and the kinetic energy have this relation where, you know, if you have all kinetic energy, then you don't have a potential. And the energies, they shift over time as your system moves. So as, you know, as the fist is moving, it starts at all potential energy, and then it slowly transitions into kinetic and potential energy until it meets the end of its path, and then it's all kinetic, let's say. So it's got this relationship, you know, kinetic and potential energy have this this finite amount of total energy that they can use. You know, and that's related to the conservation of energy. And yeah, the kinetic energy and potential energy changes as it goes along its trajectory. So the Lagrangian seeks to minimize this kinetic and potential energy. So it's kinetic minus potential. And we're trying to look for the smallest amount of energy for a particular path. And it's just really an interesting notion. And I guess just to jump back to my point, the reason I was, another reason why I was scared to touch this is because, energy is already this real crazy abstraction.
Yeah. I was actually going to touch on that because it wasn't trivial how we even got to that expression, especially the kinetic energy. Like, kinetic energy minus potential, that wasn't like a thing.
It's not super obvious,
no,
right?
It's not. No.
And honestly, I don't remember the reasoning behind why it's kinetic minus potential anyway. But
well, I mean, it was debated even. Actually, you're the one who told me this. The kinetic energy part wasn't as like, it wasn't just something that people, it's 1/2 the mass times velocity.
Right.
Yeah.
Well, this is kind of just in the realm of energy itself. They weren't even at Lagrangians at this point, I don't think. But or maybe they were, I don't know.
Well, because it all started, okay, because most introductory physics, the logical framework is you're introduced to kinetic energy and potential energy. And then you get into conservation of energy. And then the Lagrangian is a more abstract and like deeper version. And deeper version
than energy alone and the conservation of energy.
Exactly,
But they're all related in some sense. But yeah, the Lagrangian just goes that extra step further where you're like, oh God, more abstraction. But, as it goes, with more abstraction in physics, usually the more fundamental and the more deeper. So it's one of these things that you have to know because it's just so useful and it's just so it's just a deep part of how everything works basically, so you need to know it. But anyway, what was you saying?
Sorry, I was gonna say, do you remember what the answer was for that mv squared? Because when I think about kinetic energy, I think, it's like like momentum, right? And momentum's usually m mass times velocity, right?
Wait, say that one more time.
When I think about kinetic energy, it's like, it's something in motion, right?
Yeah.
And I think momentum because it's motion.
We shouldn't say it that way. I think you're saying, like, when you think of a conserved quantity, you think of momentum first, naturally, right? Yeah. Kinetic energy is not really obvious at all, right? It's like, who the hell came up with this?
Yeah.
Yeah, and it had to do with the whole argument of the vis viva controversy. We talked about this in one of our older podcasts. It's like, what is energy or something? You guys can check that one out. We can maybe link it here. But
it's a classic.
Yeah.
It's really actually, it's a really good deep dive on that. There's a lot of history and
it's a little bit of fucked up podcast though, because that was the first time we actually went ham on a script. So it kind of felt unnatural. Remember, we were kind of fucked up because we did a stupid script and it didn't work. But it actually has good information in there. So if you can really stomach the script, the information was useful. But anyway.
We were taking baby steps, okay?
Yeah.
So anyway,
we're still learning,
Yeah.
But it was like, it was cool because it showed the evolution of energy, the conservation of energy. And I think what really broke the whole system for people back in the days, saying that only momentum was conserved and screw this, other stuff. Like, they found that the conserved quantity wasn't conserved in a gravitational potential. So if you imagine just dropping a ball from point A to point B, that's not the momentum is not conserved, right? You have a delta moment, you have a change in momentum, and then some brilliant person, they found out, look at me, I found out this new quantity that actually is conserved. And you can think of that as the kinetic energy. That is conserved from point A to point B, dropping a ball on the potential. So everybody was, up in arms like, this guy found a new conserved quantity. So which one's the real vis viva or whatever, which is like this is old stuff. So all this stuff was deeply rooted in like, mysticism and religion and whatnot.
You thought energy, you thought we have a very spiritual way of talking about energy. Back then it was just probably a lot more.
Yeah, like it was intertwined with religion and God and all this stuff. So back then they were just trying to find this life or this life force or conserving force, this vis viva. And there was a big debate between momentum and kinetic energy. And long story short, we wind up using both because sometimes the kinetic energy is not conserved, and then other times the momentum's not conserved. Like, for instance, of course, the classic one with kinetic energy not conserved is inelastic collisions, right? So, and that's where the momentum's conserved, but not kinetic energy. And then, of course, like I said, the earlier example, kinetic energy is not conserved in the potential field. So so we have multiple vis viva, I guess we could say. But anyway, long story short, that's the kind of the history of kinetic energy. Then we have the potential energy, and then we found that the potential and the kinetic are actually related to each other, and they have this conservation law that just hasn't been broken so far as much as we can tell, really.
I know, and you all take it for granted.
Right. I mean, it's a beautiful law of physics, It's like kind of crazy how well it works out.
Dude, you don't even know how much I took that for granted as an undergrad, because I was just like...
Oh, we all did.
It was like, oh, you're presented with this formula. Yeah. And you're just like plug and chug.
Right.
Yeah.
Yeah, it's kind of amazing, like the history that goes behind all this stuff.
Yeah.
That they just write down an answer. It's like, okay, there you go. That's like 200 years of debate. It's kind of nuts.
Exactly.
That's why just kind of as a deviation, that's like it's kind of crazy to like be a physicist, because the knowledge that you're given is such insane amounts of knowledge that one person can handle. It's almost like you don't really deserve that knowledge because of all the legwork and all the the blood, sweat, and tears that went into actually producing that knowledge.
Exactly.
It's crazy.
Yeah.
The smartest people who have ever lived for hundreds and thousands of years, just an accumulation of all their knowledge, and you just get past in a Pearson book.
Yeah, a little morsel.
Yeah. But anyway, I keep getting on tangents here.
But anyway, no, I mean, I feel like it's necessary to contextualize a lot of the not only the expression of the Lagrangian, because it does include kinetic and potential energy, and it's like the difference of those. And the whole point of the Lagrangian is to minimize that expression, right? You're getting the difference, and then it's when we say minimize in physics, it's usually a mathematical like operation to like make that difference as close to zero as possible.
Right. Yeah. And of course, the minimization, the first thing you think of if you took calculus is to find where the slope is zero on some function, right? This is one of the key parts of calculus. Like for the laymen who aren't familiar, I mean, this is one of the most useful things you could probably ever learn when it comes out of calculus is, calculus can be used as an optimization like tool where you can find the minimal points on a graph. Let's say if you can imagine a parabola. So a parabola's minimal point would be exactly where that U shape, the bottom of that well on the U shape.
Yeah, actually, a good representation of this is if you plot energy versus time
for,
and then just like a motion where you see the kinetic energy, you see the transition between kinetic and potential. Did you have to do that in your undergrad classes? Yeah. But anyway, like
I think I know what you're talking about, but it's a little bit complicated, I think, to.
Well, let's just say that you plot energy versus time, right?
Yeah.
Over some kind of motion.
Okay.
What Terrence is getting at is that when you see one of these
wells.
Yeah.
The well's usually at the bottom of the well is the minimum potential. It's the minimal point. And you can think of it 1-to-1 as in like squared away exactly with reality. Like just imagine a valley. A valley, the way a valley looks with a dip in it, that's exactly how you would draw the potential on a potential versus time or potential versus position graph, let's say. But anyway, that's what you think of in normal calculus. But the interesting thing about the Euler-Lagrange equations is that it's actually a step above. It's another level because it uses the calculus of variations, which is, the action actually is a functional. So we're normally used to in calculus taking a point or taking some function and getting, minimal value at a point. What the action does is it actually takes in a function into a functional. So a functional is basically something that takes in functions. And then it seeks to minimize the value for that functional. So if you imagine, it's like you can imagine the different paths. It's taking all of these paths, and it just basically finds the smallest path. So a path, is a bunch of different points. So you're taking in that entire path into that functional, and then that gives you a minimal value. So that has to do with the calculus of variations.
Yeah. I mean, just not entirely obvious. I'm here scratching my head literally as like not only a body language kind of indication of where my head is at, but
right.
But also like my head itches.
But yeah, so the action is a little bit
it feels like
step up.
Yeah, it feels like it feels like you kind of glossed over the functional thing.
Yeah, the functional is just, if you imagine a normal function like sine of x.
Yeah.
Sine of x just takes in the different x values.
Yeah.
And you can plot that, and then you can, if you want to minimize that. Well, I guess that's a bad example.
Yeah.
Maybe x squared is a better one. If you minimize that, just set the derivative equal to 0, and you can find the minimal point. With the functional, you're actually taking in a bunch of different functions. So instead of sine of x, it's something else that's a functional that takes in a function. So let's imagine you took in the sine of x as one of your values instead of just a point. And then that is going to be changed into a minimal value that you find, with the Lagrangian as the kinetic minus potential energy. So you're taking in all those paths. So that is what a functional basically is. It's just, instead of taking in points, you're taking in functions into your functional.
Yeah, I remember doing this for classical mechanics.
Yeah.
Like a really rigorous proof.
Oh, did you?
But I've since
forgot it. Yeah. Oh, when we derived the Euler-lagrange equations?
Pretty much.
Yeah.
And you deal with the action, and you do like multiple orders, and I'm like, oh, okay.
Well, I was thinking about doing it for this video, but then I decided against it because I wanted to try to see if we can explain this for the audio listeners and keep it highly conceptual and not fall back on the visual aspect. So I'm trying to keep it... I'm trying to explain it as best as I can auditorially.
Good. Well, because I was trying to see examples of a functional, because
I don't know. I can't really think of an example.
Because the thing is, the gears are slowly turning. It's the end of a workday for me, so my gears are really they're rusted.
I should have got an example. I thought about that too beforehand, but I didn't look into it fast enough to get one.
But it's I thought a functional was a function within a function. It's kind of like the exhibit.
It is.
The exhibit tree. It's kind of a washed.
Yeah, I don't know. I don't even know Gen Zers would know the exhibit memes anymore. The Yo Dog meme, as otherwise known.
No, it's maybe Inception is.
Yeah. There you go.
Okay.
But I don't even know if that's true. I'd have to think about it. I was thinking about that earlier today, but I don't even know if that's true. Like I was thinking sine of x inside of sine of x.
Exactly, yeah. So I was thinking, I put a cosine in your sine.
There, yeah.
That's a function.
I don't know if that's a functional, though. I'd have to think more about it. It sounds like it is, but I don't know. I'm not entirely sure.
It's a party.
I don't want to say the wrong thing.
Right. It's a party within the party.
Yeah, I'd have to think about it more to give a solid answer, but just know it's something that takes in functions and then regurgitates an answer out or a number out. Like the Lagrangian just straight up spits out a number after you put the function in, a singular value, which would be the minimal energy. But anyway, moving on. So,
hold on. There's three. Hold on.
Oh,
this is why this is confusing, because there are three definitions according to Wikipedia.
Okay.
In modern linear algebra, it refers to a linear mapping from a vector space into its field of scalars.
Fuck that definition. Next.
In mathematical analysis, and more generally and historically, it refers to a mapping from space into real numbers or complex numbers for the purpose of establishing a calculus-like. Okay, whatever. Point is, you map. It's a function that maps into the real numbers to something that you can do calculus on, I guess. Wow, this is math.
Yeah, I don't know about
this. This is why I hate about math people doing Wikipedia stuff.
Yeah, that's what I'm saying. An example a lot of times is best. And I should have just got an example before the podcast.
And I don't want to
We
just
can
be
always
sitting
do
on my
one.
phone
We
looking
can
for
always
one.
do one in post.
Maybe so. Yeah.
Yeah,
That's
have
true.
the little computer say it.
Yeah. So audio listeners, sorry you may not hear it, but
No, you'll hear it. You'll hear it.
But anyway,
I'll make sure of it.
Okay.
well, if there is one.
I'll make it happen for you.
All right.
Well, moving on. So, I guess the other interesting things about Lagrange or the Euler-Lagrange
Let's
equations are
No, I want to see if you get into what I want to talk about.
Oh.
Go for it.
Oh, you want to see?
So I got a bunch of stuff. So, I guess one of the other interesting things about it is I had the question I actually did on Twitter. My question was, can you get any equation of motion, or does any equation of motion you can get correspond to a Lagrangian? And the answer is not super obvious. You wouldn't necessarily know immediately off the bat, I don't think. But let me rephrase that again. So it's like if you imagine the equations of motion. So the equations of motion are basically always F equals ma, various forms of F equals ma.
Is there a Lagrangian?
Mm-hmm.
Which is the expression that you put into the principle of least action and then solve with the Euler-Lagrange equations. Is there an expression for that which you can actually get an equation of motion for any system? And surprisingly, what do you think the answer is?
Well, my undergraduate brain would be like high off of, my classical mechanics.
Yeah.
Wave, my Taylor book. Be like, of course. Of course.
Right. That's all we solved.
Yeah.
Right. But of course, the answer is no.
So the answer is no.
Wah, wah, wah.
Yeah.
And one, I guess, really kind of
Feasible example you can think of is
non-conservative systems.
Right.
So for one, you can't, the normal Lagrangian is for conservative systems. But, there's things in mathematics called Lagrange multipliers and whatnot that you can actually add in if you have, let's say, dissipative forces like friction.
Damn, I forgot about those.
right.
So that's one example. And then, of course, there's the other one. But yeah, the other one is non-holonomic systems, which basically just means path-dependent systems. So that's the other example of, what Lagrangians.
God, my brain is now.
What's happening?
It's hitting bedtime for you, bro.
Damn. Well, what was I saying? Yeah. We might have to cut this.
Yeah, we will. We'll put a marker down. No, because you're saying non-holonomic, which are path dependent. So there are two limitations to the Euler-Lagrange.
Yeah.
It doesn't solve every system for you because, like I hinted at earlier, the non-conservative forces. The non-conservative forces and the non-holonomic ones, which are they're path-dependent phenomena.
Right.
Which, I can't really think of. I don't know. Can you think of something that's like a path-dependent?
Yeah, Will Kinney actually gave a good example.
He did?
Oh, he said a coin rolling on
a surface.
Why?
I guess because it's friction.
Oh, okay.
I think.
Like the ridges or something? You're just saying like flat on. Yeah.
I guess it's dissipative.
Gotcha.
I didn't think about it enough, but.
Yeah, because I was saying path dependent. I don't know what's a good colloquial way to put it. Because usually the textbook stuff is just like, imagine yourself.
It does make sense because if you imagine on a table, if you go zigzag on a table, you have more friction on that system. Whereas if you just go straight across, you have less friction. So the path really does depend on how much dissipative force you have.
I guess so, yeah.
You see what I mean?
Yeah.
Like in a gravitational well, it doesn't matter if you zigzag right.
Yeah.
Because you're not dissipating whether you zigzag left or right.
That's true, yeah.
It only matters one direction.
Yeah.
When you're on a table with friction, you really have to take into account.
You really do have to take.
Yeah. The whole path, right?
So path dependent, I think, just means in that sense.
God, my brain is slow today.
No,
I think it's just because we're doing it late.
Yeah, we are.
Yeah.
But I was thinking, something that scared us, and I was trying to conceptualize more about what the action is,
Yeah.
because the action the units for action are kind of interesting.
Ah, yes.
Energy times time.
Right.
Weird as hell.
Because usually
Joule seconds.
Joule seconds. Because you want to be able to say, I don't know. I think the natural conception is like energy per unit time.
Right.
We've had this discussion before because
I don't think on the podcast, but
I don't know. Yeah, I don't know. I'm just saying. Yeah, we've done it. We've done it maybe off the podcast,
Yeah.
but yeah, it's weird when you have units that are multiplied, right? Kind of hard to understand what that means. It's easier to understand, like if you think velocity, like meters per second, just feels real intuitive, right?
yeah.
You know, I run this amount of
Cover
distance,
this distance
in
in
this
this
amount
time.
of time.
And real clear. But I guess with multiply units, it's a little bit less intuitive, but it becomes more intuitive when it's equal something, because then you can just say like, oh, the action has a directly proportional relationship to energy and time. So when the time goes up, the action goes up. When the energy goes up, the
Action goes up as well.
but just the joule second part on its own is a little bit harder to conceptualize. But then there's also the weird property of the action, or of the Lagrangian,
Where you, or I guess the action, sorry.
where you get the energy times time, but that's actually the same dimensions.
As angular momentum, which is also fucked
Oh,
up.
I didn't even think about that.
Yeah.
Holy shit.
Right. So you're like, what the hell is going on here?
Like, what the hell?
How is angular momentum and the action have the same units? Because I think
Curious.
angular momentum is kilogram times meters per second,
Right.
and then joules is what Newton meters seconds, and newtons is kilograms meters per second squared. So then you have Newton meters squared
Per second, I believe, right? And then
oh yeah, and I'm sorry, and momentum, angular momentum is kilograms meters squared per second, so they have the same units or the same dimensions.
Curious.
so they actually don't have the same units.
This is something I thought about
Luckily, before the podcast.
because I think I would have been stuck on it for now, maybe.
Uh-huh.
But it's interesting because
It actually doesn't have the same units.
so this is one thing I've reconciled with myself a little bit better over the past few years, is that with angular phenomenon, usually with angular phenomenon, you get these overlaps with units of other things because you add in that extra radius part or something.
Yeah.
But it's really the invisible unit of radians that is the issue as well.
Oh, okay.
So with the radian, when you add in the radian into angular momentum, then it becomes different units. So it becomes kilograms meters per second times or meter squared per second radian.
Interesting.
Yeah.
So the radians are kind of fucked up. You know, we just are told to ignore it in
Undergrad, you kind of just forget about it. You're like, okay, good. I'll take anything that I can just ignore.
and you forget about it. But the radian really kind of distinguishes the angular phenomena from some of the other quantities.
True.
And I guess the radian really is kind of a unit, because if you think about it, like, what is a radian? Like, if you think pi radians, it's dimensionless, but really, if you think about it, it's circumference divided by diameter.
Yeah.
So it is something. It's just a dimensionless unit.
Yeah.
So it kind of gets lost, you know, if you really don't think about it. So when you think of angular phenomenon, you see that there's a unit that matches it. Just remember that it's a lot of times has to do with that invisible radian.
True. Damn.
Yeah.
So I reconcile that with the action. So the action and the angular momentum, while it might be cool to find some crazy relation between them, they're actually not related. It just has to do with the radian fucking everything up.
Damn. Well, that's probably, you heard it here first, probably.
Right. Well, maybe. I don't know.
Maybe as an undergrad. As an undergrad,
Yeah.
should have been like, dude.
You're blowing my
deeper
mind.
Yeah, there's a deeper connection here going on.
Right.
Yeah, because like action is one of these things that I think you just wouldn't have. I just feel like it's a much deeper conception, but I don't know. Maybe because I mean you have to think about the units for the Planck.
Joule seconds?
Yeah, Joule seconds. It's like, huh?
Yeah.
Curious.
Yeah, there is deeper you can go, right?
Yeah.
I haven't reconciled that yet.
Yeah.
Like, it is kind of strange, like, why joule seconds? And then, of course, the Planck's constant shows up in everything quantum, right?
Yeah.
And then quantum mechanics is like this extremely fundamental part of our world. You know, I mean,
Curious.
yeah, it makes you wonder, like, why? Like, why Planck's constant?
Why is this literal fundamental unit?
Yeah. So really, why joule seconds? I can't really answer that.
No, I mean, it's just a feature that it's just like, oh, we know this is the units. And some people that are like natural unit supremacists, or what are they called?
Pretty much.
They'd be like,
I like that name, natural unit supremacists.
They're just so
basically
like
theorists.
right, yeah. They're just like, don't pay any attention to that. That's
right.
Pointless to ruminate on.
Set it equals to 1 and call it a day.
No, because I mean, they might say it's pointless to ruminate on, but I think it's an interesting thing. That it's an interesting thing to ponder.
Yeah.
To think like, oh, this, the concept of action shows up at the most fundamental scale.
Right.
And like, if you want to speculate on it, I don't know. I think I can't even. Would you want to speculate?
I can't really. This is why I'm afraid to talk about the Lagrangian and Euler's Lagrange equations, because it's like it goes so deep that I think it takes a lot of mental power and understanding and sifting through equations and really thinking about these things to understand really deep stuff about it.
Yeah.
And the joule second stuff, I mean, I still don't really know what to make of
I'm going to
that,
speculate.
Really. Okay.
I'm going to speculate.
All right.
Especially with like...
Juan's going out on a limb here.
Please don't crucify me for this. No, but in the sort of things that I've kind of been cooking up in my head, I was thinking, well, like action kind of seems like it's almost like this kind of ties into information, but it's like weird that it's something that happens in time.
Okay.
I don't know. And then the fact that it's like the Planck scale, it's at or let's just entertain the thought that, it's not just a units thing that just happens conveniently to work out.
Right, right. You're saying the unit somehow is like some fundamental.
Let's assume it's a fundamental
Let's think
thing.
of it like that. Yeah, because the Planck's I think that's fair, because the Planck's constant itself is a mysterious constant, and it is fundamental in so many things.
Yeah.
In quantum mechanics.
What if that's like a carrier thing? In my head, I'm speculating, but I'm like, oh, maybe what if it's like this thing that's maybe relaying something as a carrier? I don't know.
Like it's carrying some kind of information, you're saying?
I don't know. Hey, just throwing it out there.
It's literally the quantity of quantum. Like h bar is literally everything in quantum, right?
Hey,
it's everywhere.
It's quantum. What do you want me to do here? It's the Planck's constant. He's like walking through the door. Oh, here we go. Shit's about to get quantum. That's a t-shirt.
Pretty much.
That's a t-shirt. It's like
right.
H bar showing up.
That's pretty good. H bar's walking in the bar.
Dude, oh shit. H is wait, hold on. Did you say H is walking to a bar?
No, I didn't say that, but
that's a good idea too.
So an H, that's a good physics joke. So an H walks into a bar.
There's something there.
You can finish it in the comments.
Yeah. But yeah. Anyway, that's an aside. That's the speculation corner. I think there is something interesting, and I know we've kind of had conversations about it.
Right.
In the school library at some point.
Yeah. Well, I guess, did you want to know some more interesting things I thought about it with it? So I guess the other thing that I had on my list with the Euler-Lagrange equation is the whole fact of why Lagrangian for class mech, why Lagrangian for quantum field theory, why no Lagrangian for quantum mechanics?
Interesting.
So that's another question where you're like, because you think of it as this real deep fundamental thing.
Mm-hmm.
So you're saying, I use Lagrangian all day in classical mechanics. I mean, Lagrangian in classical mechanics is like a godsend, right?
Oh,
because you can just become a lazy ass mofo and just solve anything with the Lagrange equations after a while.
The hardest part is finding the coordinate system that
Yeah.
That'll make this problem easy.
Right.
Yeah.
And then once you got that, I mean,
you got the undergrads will definitely know. I mean, once you've got your Lagrange equations down for class mech, I mean,
it's trivial.
Yeah, it's like you can solve all the problems basically just without thinking, basically.
Yeah, I mean that was a problem with me. I'd be like, okay, now that I have the right expression, do I really want to finish it though?
Yeah, it's almost too easy because it just takes away all ability to think about intuition and everything.
Yeah.
You just once you've got the kinetic energy and the potential energy, that's it. That's all you need.
Yeah.
So then you can just solve the Lagrangian. That's it. But then you go to quantum mechanics and we use the Hamiltonian. And you're like, what the fuck, man? I used all this Lagrangian in classical mechanics. Why do I have to stay with the Hamiltonian now and restart my whole game?
Yeah.
But then you're like, it's fine, I guess, because you're always using the Hamiltonian in quantum mechanics.
Yeah,
and
you're
you just
like
kind of forget
minus,
about the Lagrangian.
Yeah, you're like minus, plus, what's the difference?
Yeah.
It's all the same to me.
One is being funny a little bit because there's differences, but yeah, I mean that's basically what it is. You're like, I got used to the Hamiltonian, now the quantum, I'm fine.
Well,
and then there's a switch again. So I'm not familiar with this. You might be more privy to it.
Sure.
But
What's up?
they switch back to the Lagrangian in quantum field theory.
Yeah, they do. Yeah.
So the quantum field theory, they go hard on the Lagrangian. And I guess they probably, I don't know if they use Hamiltonian as well, I imagine.
I think it depends on the. It's more contextual. It depends.
Yeah, okay. But the Lagrangian, I think, is predominant in quantum
QFT,
field theory.
it is built on it.
So then you got to ask, like, is it possible to use the Lagrangian in quantum mechanics? And what would you say, Juan? Do you have an answer?
Speculating. Well, let me not speculate. Let me actually take in the I'm taking in the information that you gave in earlier.
Yeah.
That you gave me earlier.
All right.
And I'm assessing the information, and I'm gonna say, you can't. It's very difficult to use because the Lagrangians have to do with path stuff.
Okay.
And quantum, can you even say anything about paths?
Okay. So that's interesting thoughts. And you're right in the sense that it does have to do with path stuff, but you actually can use the Lagrangian in quantum mechanics.
Thank you, Richard Feynman.
Yep.
You got it. So the path integral formulation.
Yeah, dude.
So the path integral formulation is what they use for Lagrange mechanics in quantum mechanics, just like in quantum field theory. And I guess they don't teach it to undergraduates because it just adds unnecessary complication when you could just make life so easy just knowing the Hamiltonian. But yeah, you can use Lagrange mechanics in quantum mechanics, normal quantum mechanics, not relativistic. And you do just like in quantum field theory, I think, where you take all the paths and you produce these probability amplitudes. And then I guess the biggest probability amplitude or whatever it is, I forget what it is exactly, will give you that path for that quantum system. That's all I can tell you because I don't know how to do it. I've never done the path integral, but it is possible.
Yeah, and the easiest way is just throw Schrodinger's equation at the kids.
Right.
Because it's a
right, because it's simple, right?
Yeah. And the
Don't
Schrodinger,
overthink it.
For those of you folks listening, the Hamiltonian, it's used explicitly in the Schrodinger equation.
Yeah.
It's very succinctly summarized as, what do they have? Psi, the wave function times h. Well, not times, but
It's just kinetic plus potential
Yeah.
with a wave function attached.
Yeah, but if you ever see that in a T-shirt, it's what it is.
Yeah.
And some people try to boast. I've seen some people with that
Really?
the tattoo, like
Posers.
I've seen people with the tattoos of like the Schrodinger's equation. I'm like, really?
Well, they probably got it when they were young.
Hey, if you got it, I'm sorry. I'm not really.
Yeah, no hate.
No hate.
It's kind of like the e to the I plus 1. You know, the e to the I pi plus 1 equals 0.
Yeah.
Everybody gets that when they learn Euler's formula for the first time in undergraduate.
I mean, it is pretty brilliant, but
It is, but it's such a common tattoo.
That or Maxwell's equations. I mean, those are all the kind of standard ones that you see everywhere.
I want to see somebody with some really. What would you say? What would be the best equation to get a tattoo of?
Ooh.
Maybe
You don't see the Euler-Lagrange that often.
You don't.
I haven't seen that really, and that's like
Get it
one of
as a
number
tramp
one.
stamp.
Yeah. Damn.
if you're cool enough to get a tramp
stamp of Euler-Lagrange,
so
you're good in my book.
Yeah. So when you're your professor lecturing and your shirt kind of rolls up a little bit, so the students can see.
If anybody's a tramp stamp of Euler-Lagrange equations,
please send a picture somehow to us. We will put it on the podcast.
You would definitely be a Giga Chad.
Or like, you know how people get those like gangster tattoos of like I don't know, on this chest tattoos.
We need more physics gangster tattoos.
Euler-Lagrange for life. Yeah, or something. Anyway, I think it would. I think what's underrated, if you're thinking about a physics tattoo, is Maxwell's equations in the not the tensor formulation. What is it called? The
integral formulation?
No, the
Oh yeah, you mean the
F mu nu.
Yeah.
What was it?
That you can have a Lagrangian for that. There's a Lagrangian for the You're right though. It's the Maxwell stress energy tensor.
Oh, okay, yeah, man.
Yeah.
Okay, yeah,
That's high level.
Get that one. That's a cool one.
Or get the
standard model Lagrangian on your chest.
The full expression.
This is my Bible. Right. It's just like
not the reduced version, the full version. That would be gangster.
That's a back tattoo for sure.
Yeah.
TSA will not let you fly. Like, what is all this?
Right. This Arabic. Actually, maybe I'll cut that.
Well, it's Greek. So, but I wouldn't put it past TSA agents.
Yeah.
To be like.
Well, you know that one guy got kicked off the plane because a woman saw him writing Arabic,
but he was writing.
No,
she thought Arabic, but he was doing math equations, like
Yeah, he was a black man.
Yeah. Okay.
Yeah. He was a black man doing calculus.
And
that was threatening for her.
I'd probably call the cops too.
I was gonna make a joke, but I'm not gonna go there.
Anyway.
Yeah.
So I guess
but the Lagrangian goes to the highest level.
Right. So if you want to be the ultimate laziest physicist and just shortcut your path to physics, just learn the Lagrangian for everything.
Mm-hmm.
Learn the Lagrangian for class mech. Learn the Lagrangian for quantum mechanics. Learn the Lagrangian for quantum field theory. Learn the Lagrangian for electromagnetism as well.
Wait, what?
The stress energy tensor. You can derive all the Maxwell's equations from Lagrangian.
Yes.
Just learn the Lagrangian. That's all you need in life.
Yeah, we're Lagrangian maximalists.
Yeah.
Here at the Eigenbros.
If you want to be a full Pareto principle man or woman, learn the Lagrangian and just skip all of physics.
It's probably horrible advice.
No, I mean,
but I'm saying if you want to just speed run physics, just learn the Lagrangian for everything.
I mean, it's all built on the back of the principle of least action.
Yeah.
Like, that's the fundamental core tenet of what we do here in
so
physics.
That just means you're straight up
following the principle of least action by only learning the Lagrangian.
Yeah. And at the Lagrangian office, we have a sign that says, days since the last time the Lagrangian has failed us, and guess how many days it's been. Well,
imagine never.
Well, only if there are no,
unless it's non-holonomic.
Or non-conservative. But we don't deal with those kind of people.
Yeah.
Or those systems are not welcome at that place. But I mean, you do see it at the highest levels. You see it at the whatchamacallit, the damn, man, why am I blanking on the name?
Yeah.
You were just saying it. The huge the huge equation.
Oh, the standard model Lagrangian.
Thank you.
Yeah.
Man, the standard model Lagrangian.
The Lagrangian is everything. It is the equation you use to get everything.
Yeah.
In theory.
Yeah.
But anyway, do you want to learn another one?
Yeah, man. I'm learning new shit today.
Yeah. I mean, this is all the stuff I learned. I was like, shit.
Hell yeah.
I feel like I should have known some of this, but I'm like, I mean, we all learn at our own pace, right?
Yeah.
But another thing is, this was interesting that I was reading the Feynman lectures, and he actually had an interesting way of a parallel with the principle of least action.
Mm-hmm.
So I was like, the calculus of variations, it's like, is that just invented for the Lagrangian? Like,
what other things are there?
And then it's interesting because optics also has a principle of least time.
It does.
Which is it parallels a lot of what the Lagrange or what the principle of least action is. So if you have some trouble kind of intuitively understanding the principle of least action, you can kind of get a little bit more grounding by analyzing the principle of least time. And that's one of these interesting things with optics, where basically what it says is the optics. What would you say? That's a good way to say it. Like the light ray travels to its destination in the least amount of time, essentially. So with the principle of least time, if you imagine like a light ray bouncing off the surface, it's not necessarily obvious which path it's going to take if you just have if you have multiple different paths. So you can look at all the different paths that it can take from A to B, and it's just the path that's going to take the least time. And you can kind of do that more intuitively and actually sketch out the rays and measure the lengths of them, and then see which one has, the least distance, I guess, which should take the least amount of time. And that's just another aside I wanted to put out there, just to see if you wanted to understand, I guess, better the principle of least action. It actually can sometimes be more beneficial to start with something more grounded in in reality, because the principle of least action is really abstract. So if you go with the principle of least time with the optics
version, it might help.
Is that how he came up with this formulation? What helped him kind of come up?
That's what helped him motivate the principle of least action in his Feynman lectures. I don't know if if that was for the path integral. It might have helped.
Well, because he was really thinking about this.
Yeah, it's steep.
His path integral formulation kind of helped with develop. I mean, he helped develop quantum chromodynamics.
Yeah. Or QED, I think, was one of his.
Oh, my bad. QED.
Yeah.
Quantum electrodynamics.
Yeah.
Well, I guess maybe it's a subset of quantum chromodynamics. Who
knows?
Well,
no, it's different because quantum chromodynamics has to do with gluons, gluon interactions and stuff, color charge.
Mm-hmm. I think he might have contributed to it, though.
I just know that one of his main claims of fame is electrodynamics, the quantum electrodynamics.
Yeah, but it's because of the path integral, though.
Yeah.
His path integral formulation.
Yeah, I think you're right. Yeah.
Was it's called the Feynman path.
Yeah. Right.
But I mean, if you want, I think he's actually a great person to probably go to this, see if he's written a lecture or something about it, because he obviously thought about it for a very long time.
Well, he did. This is the Feynman lectures that I was talking about.
Oh, really?
The principle of
least
action. Yeah.
I'm saying, even in a larger sense, like if he's had, I don't know if you scoped the entirety of I guess more thoughts on how he helped develop the.
Oh, you mean like more of an informal thing where he's like interviewing or something?
Yeah.
No,
or doing a lecture on
interestingly enough,
his path integral formulation thing.
No, interestingly enough, though, Steven Strogatz on Twitter posted a whole shitload of archive and interviews on Feynman. And it's probably some of the deepest interviews
that he has available. Yeah,
and then I don't think they're common knowledge either. But it's all annotated, so you have to read through it. No video or anything, but I would imagine if you wanted to try and see that probably might be your best bet. I think it might be on AIP or something, one of their archives or something. If you want to check that out, I wanted to look through it, but I just didn't have enough time to look through all that.
Yeah,
but yeah,
you're like, I'm not going to read all that.
TLDR.
No, but he's a great source. I mean, I didn't even think about that. He's because I mean, he won. Did he win the Nobel Prize for that? I mean, it definitely.
I think you might be right.
Him.
I'm not sure.
I actually don't know what Feynman got the Nobel Prize. It's pretty bad. I do not know. It might have been though.
I think it was. I read his biography. Surely you're joking, or biographies.
Yeah.
And they're sort of semi-autobiographical, but he's still. You kind of get a good sense of how he thought. He really thought about physics a lot.
Right.
And in a real physical, not in a sort of hoity-toity
way.
Yeah, not in a sort of layers of abstraction upon layers of abstraction.
There's nothing wrong with that. I mean, some people are more mathematical, abstractionists. But Feynman's approach was very much try to keep it simple and as grounded in reality as possible, which is heavily I heavily identify with that because I think that's just it just helps to really keep things simple, and you can have insane insights just with very simple analogies, right? Which you can't get with overly complicated. Well, I guess not overly complicated, but just sometimes simplicity is the way to go over complexity.
Yeah. Well, damn. Now I'm interested to go see more about how he kind of formulated his thinking because I mean, he's somebody who thought about this really deeply.
Yeah. It's kind of
action
crazy
stuff. Yeah.
Yeah.
To help formulate the current formulation of the Lagrangian, quantum field theory.
Yeah.
Yeah.
I mean, that's the height of modern physics, pretty much.
Yep.
But yeah, I guess let's see, what's our time? Yeah, to sum up, one of the last other pieces that I kind of wanted to touch upon was, we always hear the principle of least action, but really that's kind of wrong because you're really supposed to say the principle of stationary action. So I don't know if you're familiar with that, but the principle of stationary action is just another little part of this thing where you have to clean up your understanding of the action.
Yeah.
Because we seek to minimize the energy, but actually that's not really true. With the stationary action, you actually can get a minimized, a maximized, or a saddle point. So just wanted to clear that up as well, and that may not be exactly obvious. I still don't really understand it myself fully. But I guess with the calculus of variations, you can You can either get a maximum, a minimum, or a stationary point, or a saddle point. And it doesn't necessarily have to be a minimum. But I guess a saddle kind of makes sense because, we talked about before, like these, what was it called? Like these spontaneous symmetry breaking things. Sometimes things are in non-equilibrium states, right? They may be sitting on a saddle point where they want to fall down into something. So it might be minimized for that point, but it might go to another energy state soon after. So the saddle point could be a thing as well, and you're not necessarily minimizing the action. You're just minimizing to see that saddle point in the expression. But yeah, did you have any other final thoughts about the Euler-Lagrange equations or the action, principle least action?
I learned a lot today.
Good. I'm glad. I really thought about this one all week, so.
Dang. Crazy. I hope you listeners kind of got a good sense of all this because, hey, all those things you said,
your mind's blown.
Well, this just shows you how much of a fear I have for this topic because it's just so deep and it's just so abstract and so fundamental in physics. Like even with that stuff, that all these points of knowledge that I found or weaknesses in my understanding, I still don't feel like I understand it fully still. Like I still feel like I need more to understand it. And it just shows you how crazily deep the action is, the principle of least action is.
I mean, because like honestly, the treatment of the action from a lot of my courses was just it's
shut up and calculate.
It's this but it's like on a layer of it's very abstracted. And I was aware about the saddle point stuff and the whatever. I think it's a technicality that I think our professor
they usually gloss over it and say least action, but if you want to be completely accurate, you really have to say principle of stationary action. Yeah. Because you have to include maxima and saddle points as well.
Mm-hmm. Yeah, one time the professor gave us this problem for a homework that was like basically just a whole homework dedicated to like action and looking at it. Okay, you do find you try to find the minima, but then you do see that you see all the what is the word I'm looking for? Caveats?
Yeah, caveats, yeah.
Yeah, and you run into like these problems, you're like, okay, and you kind of get a more abstract understanding of it, but it's still very much like you
can't really internalize it fully.
Yeah, because you want to tie it into something a lot more
tangible.
Yeah.
That's the problem with these abstractions. You got to somehow relate it to, my tactic is always to try to bring these abstractions to reality. So you have to have a bunch of examples. Examples are underrated.
Mm-hmm.
People don't nearly use as many examples as they should, especially in the rigorous sciences. Mathematicians can get caught up in their own asses all day with rigor. It's like, just use an example. Examples are underrated. Use them.
Mm-hmm.
And then, of course, the other one is just to keep it practical and physical. So make nice, simple, conceptual arguments. And you can get a lot from that. You just got to bring it close to reality, because, humans, that's our mode of thinking. Mm-hmm. Abstraction is kind of unnatural. I mean, I don't know if we're built to really understand this stuff.
Yeah, no.
Like, it's almost like we kind of got lucky cracking this mathematical code, and we're trying to look at these things like, these equations and whatnot, and then speaking the language of the gods. Like, we don't have the brain capacity to really understand this stuff at any deep level.
I mean,
it's kind of a miracle we even came up with any of this stuff.
I know, we're just monkeys scratching our heads.
Yeah.
Scratching our butts with chalk between our fingers. I mean, under our nails. Sorry.
Probably everywhere.
Probably.
Physicists walking out all day with chalk all over their pants and their
chalk
shirt.
all over the pants.
Everywhere.
A Lagrangian tramp stamp. Trying to hide it under your tweed suit.
The patches on the elbow.
Yeah. Yeah. Anyway, we hope you folks really liked and enjoyed this episode. Don't forget
a little scatterbrain.
Hey, it's fine, but don't forget to like, share, comment, and subscribe.
Yes, guys, and check out the website, Eigenbros.com, Eigenbros on Instagram, Eigenbros on Twitter, Eigenbros2 on TikTok, and then patrons, guys, we thank you, and we greatly appreciate the support. And if you guys want to become Patreon members, patreon.com/Eigenbros. Me and Juan will do a 30-minute podcast there, random topics,
and we're trying to do hangouts consistently, but
we'll see. We got to figure out all our schedules.
Yeah, we got to figure out our schedule stuff, but we want to do one.
Yeah.
Yeah.
Hopefully, have another one soon.
Yeah, for sure this week. Well, hopefully one happened this week.
Yeah.
We'll see.
Or will happen, but
it's the holidays.
Yeah, true. And we'll figure it out.
And we'll figure it out. But anyway, folks, look forward to the next one.
Mm-hmm.
And I'm thinking this next one's going to be a big one.
You think?
For me, at least.
Why is that?
Because
spoiler
alert! It's going to be Terrence, you swung for the fences on this one.
Oh, you're gonna crank out something, huh?
I'm gonna try.
Sweet.
I'm sleepy.
We'll see.
You got sleepy.
Now you got
Juan.
the pressures on.
You got sleepy Juan on this episode.
I think we're both kind of sleepy, man. I don't know why.
Maybe because I drove today.
Yeah.
From a state across.
So.
Yeah. Old Sleepy Joe, me. That's my middle name, Sleepy Joe. But anyway, folks, tell us honestly, the interesting fact that you picked out from this episode.
Yeah.
Or
if you have any more interesting
were.
facts on Euler-lagrange. I mean, this
stuff keeps going, bro.
Yeah, it's a fractal.
Yeah.
It keeps
fractal mind-blowing.
But yeah,
anyway, let's not trail off.
Yeah, let's not trail off. But anyway, we'll see you later, folks.
Ta-ta.
Bye-bye.